Welcome to the Cosmic Journey, where science meets imagination. Today, we're diving deep into the universe's mysteries with a groundbreaking discovery that challenges everything we thought we knew. The James Webb Space Telescope, JWST, has revealed thousands of galaxies that look eerily similar to our own Milky Way and might just rewrite the story of the cosmos. Stick around as we explore the implications of these findings and ask the question, is the universe really 27 billion years old? Galaxies in the early universe appeared far more chaotic than those we observe closer to our own time. For a long time, researchers believed that the tumultuous conditions and frequent collisions in the early cosmos would prevent galaxies from developing their elegant shapes. Contrary to this belief, the James Webb Space Telescope, JWST, has revolutionized our perspective by uncovering thousands of galaxies that resemble the Milky Way, existing much earlier than previously thought. This discovery challenges our previous understanding and significantly alters our views on how the first galaxies formed and evolved over the past 10 billion years. Today, we explore how the James Webb Space Telescope has transformed our comprehension of the universe's infancy. For the first 380,000 years following the Big Bang, the universe was a scorching, dense blend of protons, electrons, and other elementary particles, along with light elements. As the universe expanded, it cooled down, enabling protons and electrons to come together to form atoms. The early universe was primarily composed of hydrogen, its heavier isotope deuterium, helium isotopes, and a trace amount of lithium, setting the stage for the cosmic evolution that followed. Stars didn't appear in the universe until it was about 100 million years old, a span longer than the period since dinosaurs went extinct. During this era, there were no stars, galaxies, or any luminous objects. Astronomers are gradually uncovering how the universe's very first stars, known as population III stars, emerged from this primordial darkness. A key piece of evidence comes from the cosmic microwave background, CMB, which is relic radiation left over from the universe's hot, young phase. Computer simulations suggest that density variations in the early cosmos served as seeds for the formation of massive gas clouds. Gravity drew these fluctuations together, creating focal points where gas could accumulate. As these clouds gathered and condensed, they warmed, leading to the formation of hydrogen molecules. As the temperature within these clouds fell, denser clumps began to form, becoming hundreds of times more massive than our Sun. These clumps were able to resist splitting due to outward radiation pressure, enabling the birth of massive singular stars from each dense region. The first stars to light up the cosmos were giants, with sizes ranging from several tens to over 1,000 times the mass of the Sun, shining with a brilliance potentially millions of times greater than our Sun. Over time, the gravitational influence of these luminous stars drew others close, leading to the creation of the universe's earliest galaxies. Unlike the complex galaxies we observe today, these initial formations were simpler, primarily consisting of hydrogen and helium gas. As the stars within these early galaxies underwent nuclear fusion, they synthesized heavier elements, seeding these galaxies with the essential components for life. These first galaxies were less organized and smaller than those we see in the present day, making them difficult to observe. With the James Webb Space Telescope, we are now able to explore these long-standing questions about the universe's earliest galaxies, including their formation time, size, appearance, and their role as the precursors to modern galaxies. James Webb's capability to capture faint and distant galaxies in infrared is crucial for verifying the distances to galaxies that were instrumental in these early cosmic processes. Considering the universe's age of 13.8 billion years and the vast distances of these early galaxies, powerful infrared telescopes like James Webb are indispensable for their detection. Prior to Webb, the distant galaxies we could observe were those that were bright and large, limited by the capabilities of past telescopes. The James Webb Space Telescope's JWST enhanced sensitivity has revolutionized our ability to detect fainter and smaller galaxies, challenging our earlier notions about the universe's infancy. Interestingly, it is these less luminous galaxies that are far more abundant and crucial, likely playing a key role in the reionization process, rather than the brighter ones. This shift in focus towards faint galaxies for study is analogous to understanding human evolution by examining entire populations instead of just a few exceptionally tall individuals. JWST's capabilities allow us to delve deeper into the early universe's mysteries. In a groundbreaking revelation, the James Webb Space Telescope, acting as a supreme time machine, has astonished the scientific community by uncovering over 1,000 galaxies bearing a striking resemblance to our own Milky Way, hidden deep within the early universe. These galaxies, resembling warped vinyl records with their intricate spiral arms, were discovered more than 10 billion years in the past, defying the previously held belief that frequent galactic collisions during that era would prevent the formation of such delicately structured galaxies. This finding challenges our understanding of galaxy formation in the universe's early stages. Contrary to previous beliefs, disk galaxies were found to be 10 times more prevalent in the early universe than astronomers had anticipated, a revelation brought to light by recent research. This surprising discovery, among others made by the James Webb Space Telescope, JWST, adds depth to the enigma of how large galaxies and potentially life first emerged. These findings were detailed in the Astrophysical Journal, with Leonardo Ferra, an astronomer at the University of Victoria in British Columbia, Canada, leading the study. For decades, disk galaxies were thought to be scarce due to their frequent, violent encounters in the cosmos. The JWST's ability to uncover a multitude of these galaxies signals its remarkable capabilities and indicates that galaxy structures formed much earlier than previously thought. Historically, galaxy formation theories posited that the universe's earliest star clusters evolved into dwarf galaxies, which then grew into larger galaxies through a process of cannibalization and violent mergers. This process, believed to take place over 10 billion years, led to the formation of large galaxies similar to the Milky Way, a disk galaxy with spiral arms and a flattened shape, which is commonplace today. However, in the densely packed early universe, filled with dwarf galaxies, it was assumed that galaxies resembling the Milky Way would be quickly distorted. The JWST's observations challenged this assumption, suggesting a much earlier formation of complex galaxy structures. An observation spanning 9 to 13 billion years into the past examined 3,956 galaxies, revealing that 1,672 of them were disk galaxies similar to the Milky Way, existing even when the universe was merely a few billion years old. Christopher Canellis, a co-author of the study and a professor of extragalactic astronomy at the University of Manchester, pointed out that prior to the James Webb Space Telescope, JWST disk galaxies were believed to be almost non-existent until the universe reached about 6 billion years of age. The findings from JWST advanced the formation period of Milky Way-like galaxies to nearly the dawn of the universe, significantly altering our comprehension of galaxy formation. These insights compel astronomers to revise our theories on the early galaxy formation and the evolutionary processes of galaxies over the last 10 billion years. Living in a disk galaxy, which may indicate conditions conducive to the emergence of life, suggests the possibility that life could have begun earlier in the universe than previously believed. Beyond redefining our views on early galaxies, the JWST has also uncovered challenges in studying the atmospheres of planets within the TRAPPIST-1 system due to the intense activity on the surface of its central red dwarf star, complicating observations. In March 2023, the James Webb Space Telescope, JWST, utilized its mid-infrared instrument to observe the secondary transit of TRAPPIST-1b, indicating that it likely resembles a bare rock without an atmosphere, exhibiting a surface temperature of approximately 232 C 450 Fe similar observations were made for TRAPPIST-1c. In a pioneering effort by Olivia Lim and her team at the University of Montreal, new observations were made, marking a significant achievement, the first ever spectral analysis of TRAPPIST-1b. These groundbreaking results have offered new insights into the atmospheric composition of TRAPPIST-1b. Contrary to initial expectations, the findings did not present any substantial evidence of a dense, hydrogen-rich atmosphere surrounding TRAPPIST-1b. This revelation challenges prior assumptions and introduces additional complexity to our understanding of the exoplanet's atmospheric characteristics. It's important to emphasize that the lack of a dense hydrogen atmosphere doesn't categorically rule out the presence of an atmosphere at all. The data implies that TRAPPIST-1b could still host a thinner atmosphere, which remains a point of interest for further investigation. Reaching definitive conclusions about TRAPPIST-1b's atmospheric conditions continues to be challenging, casting an intriguing shadow of uncertainty over the initial findings and calling for more thorough investigation and analysis. This compelling aspect of the research highlights the need for further study to demystify the atmospheric properties of TRAPPIST-1b. As the scientific community navigates through these unanticipated findings, the drive to understand the complexities of exoplanet atmospheres is invigorated. Delving into the atmospheric makeup of TRAPPIST-1b not only deepens our knowledge of this particular exoplanet, but also aids in the wider quest to explore the varied atmospheric dynamics of planets beyond our solar system. The mystery of TRAPPIST-1b's atmosphere invites scientists to further explore the nuances of exoplanetary atmospheres, setting the stage for future advancements and discoveries in the enthralling field of exoplanetary science. According to team member Ryan McDonald from the University of Michigan, the star TRAPPIST-1 has a profound and overarching influence on observations, a factor that likely affects other planets in the system similarly. This suggests that the tumultuous nature of the host red dwarf star could be complicating efforts to accurately assess the atmospheres of its orbiting planets. The quest to determine the habitability of TRAPPIST-1 is complicated by challenges in analyzing its planet's atmospheres. The technique of transmission spectroscopy is crucial for this endeavor. This method involves observing the light of a star as it passes through the atmosphere of a planet during its transit across the star from our perspective on Earth. If the planet possesses an atmosphere, some of the starlight will filter through it, allowing molecules within the atmosphere to absorb light at specific wavelengths. By examining the absorption lines in the spectrum of the planet, scientists can identify the atmospheric gases present. However, studying planets orbiting red dwarf stars like TRAPPIST-1 presents additional challenges. Red dwarfs are known for their active natures, exhibiting bright flares and large dark star spots, which can significantly interfere with the spectral analysis. These stellar features can create misleading bright and dark lines in the spectrum, mimicking the absorption lines and leading to potential misinterpretations. Moreover, the presence of stellar flares' sudden and unpredictable brightening events can alter the intensity of the star's light, complicating the accurate measurement of the portion blocked by the planet. To navigate these complexities, a comprehensive and nuanced strategy is required. The research team must account for and adjust their methods to mitigate the impact of these stellar phenomena on their observations, ensuring a more accurate understanding of the atmospheric compositions of TRAPPIST-1's planets and their potential habitability. The research team utilized advanced modeling techniques to navigate the challenges posed by the dynamic stellar activity on TRAPPIST-1's surface. Two primary approaches were adopted to address the complexities found in the observational data. The first approach involved detailed modeling of the stellar activity on TRAPPIST-1, followed by the removal of this stellar influence from the collected data before a thorough analysis. This method aimed to clearly separate the effects of the exoplanet's atmosphere from the variable behavior of the star, allowing for a clearer examination of the atmospheric signatures. Concurrently, the second strategy adopted a more integrated approach, simultaneously modeling the stellar activity's contamination effects and the potential atmospheric characteristics of TRAPPIST-1b. This holistic modeling was designed to achieve a comprehensive understanding of how the star's activity and the exoplanet's atmospheric features might interact and be reflected in the observed spectrum. Remarkably, the results obtained from both modeling strategies led to a consistent and compelling finding, highlighting the nuanced approach needed to interpret the data accurately and the sophisticated methods employed to overcome the challenges of stellar activity in the pursuit of understanding. Exoplanet atmospheres. Contrary to the expected presence of a thick hydrogen atmosphere, the spectrum observed for TRAPPIST-1b could be fully explained by the star's activity. This revelation challenges the prevailing beliefs regarding TRAPPIST-1b's atmospheric makeup and highlights the significant influence of stellar phenomena on the observed characteristics of the planet. As the scientific community digests this surprising development, the implications of these findings reach far beyond TRAPPIST-1b, offering crucial insights into the study of exoplanetary atmospheres at large. The agreement between results from various modeling techniques strengthens the reliability of these conclusions, showcasing the complexity of dissecting the atmospheric signatures of distant planets. This detailed investigation exemplifies the rigorous and innovative strategies adopted by researchers, setting the stage for a more profound comprehension of exoplanet atmospheric behaviors across the universe. TRAPPIST-1b, among the 7 planets in the TRAPPIST-1 system, emerges as the most likely candidate to lack an atmosphere, considering its vulnerability to the star's stellar wind and potent flares that could erode any atmospheric layer. This insight, however, is part of a broader endeavor to determine the atmospheric conditions and potential habitability of exoplanets, underscoring the nuanced challenges faced in this exciting field of astronomical research. Determining whether the planet harbors a thin atmosphere composed of water vapor, carbon dioxide, or methane poses considerable challenges due to uncertainties stemming from the activity of the star. This complicates the observation of spectra for other planets within the system. Ryan McDonald, a member of the team, stresses the importance of addressing the star's influence, particularly when studying planets within the habitable zone, such as TRAPPIST-1d, E, and F. In a separate endeavor aimed at unraveling the mysteries of the universe, images captured by the James Webb Space Telescope, JWST, have revealed the most distant example of an Einstein ring to date. This extraordinary halo of warped light, situated an astounding 21 billion light-years away, encircles a mysterious and dense galaxy. Einstein rings are a rare phenomenon predicted by Albert Einstein's theory of relativity. Gravitational lensing, caused by the immense gravity of a foreground object, distorts space-time, causing light from more distant objects to appear curved and bent. This effect magnifies the light of the lensed object, facilitating detailed study. While most gravitationally lensed objects manifest as arcs or partial rings, a genuine Einstein ring forms a complete circle when the distant object, foreground object, and observer are perfectly aligned. In a recent study, uploaded to the preprint server Arxiv and accepted for publication in the journal Nature, researchers provided further insights into this remarkable discovery. Gravitational lensing was employed to capture images of the most distant star ever detected and one of the oldest galaxies in the universe. The James Webb Space Telescope, with its $10 billion price tag, stands as one of the most ambitious engineering endeavors ever undertaken. Its capacity to explore and capture ancient cosmic history resonates with the fundamental questions that have captivated astronomers for decades. The telescope's capability to unveil the deep cosmic past, bridging the early epochs post-Big Bang to our present existence, represents a remarkable feat. Our connection to the cosmos, rooted in our material origins, underscores the significance of exploring cosmic history as a window into both our individual and collective pasts. We owe a debt of gratitude to the scientists and engineers behind the James Webb Space Telescope, whose successful deployment has elevated it to the status of the most powerful observatory, empowering cosmologists to delve into the ancient annals of the universe. just as we reflect on the histories of civilizations like the Greeks and Romans, whose existence seems but a fleeting moment ago, we now have the unprecedented opportunity to unravel the narrative of our universe, the history of everything. Our existence, intricately woven from the fabric of star stuff, establishes an unbreakable link to the vast cosmos that surrounds us. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.